The multi-choice section now. First question, a continuous stream of water falls through a vertical distance of 100 meters. Assume that no thermal energy is transferred to the surroundings. Specific heat capacity of water is blah. What is the temperature difference between the water at the top and the bottom? Okay, so the thing that you need to figure out on this one is the idea that the energy of the fall in water there is all converted into heat by the bottom. So you have to equate the heat that's gained by the falling water to the loss in gravitational potential energy. So we'll do that. So mg delta H is equal to mc delta theta, specific heat capacity equation there. The masses cancel because all of the water gets the same amount of heat on its way down, which is good. So that doesn't depend on the amount of water that falls. And so we're looking for delta theta. Delta theta is equal to G delta H over C. So 9.81 times by delta H is 100 divided by 4,200. Everything's in base units, so that's okay. So we get out B. A student measures the power of a microwave oven, places 0.2 kilograms at 23 degrees Celsius, and it heats for 1 minute, so that's 60 seconds, and it heats it to that. So delta theta is that, take away that, which is 56 degrees. Okay, what's the average rate at which energy is gained by the water? So power, which is the rate of energy transfer, is E divided by T, and the energy is same as over here, mc delta theta divided by T. So we put all those numbers in. So we've got the mass is 0.2 times by 4,200 times by delta theta, which was 56, divided by the time 60 is this one, to two significant figures. Composition of carbon dioxide is that. So how many molecules are there in that much of the gas? So first of all, we need to find the number of moles that there are in the gas, and once we've done that, we can just times by Avogadro's number. So to work out the number of moles, we do the number of moles is equal to the mass of the gas in grams divided by the relative atomic mass. This is a different one. You don't want this in kilograms, you want it in grams. So then we have the total number of molecules is that times by Avogadro's number. So that's that times by Avogadro's number. So we just need to add this up. We've got a carbon and 2 oxygens is 3244, isn't it? So mass in grams, 2,200 divided by 44 gives us 50 moles. Then we need to times that by Avogadro's number, which is 6.02 times 10 to the 23, which gives us 3 times 10 to the 25, so it's C there. What's the total internal energy of 2.4 moles of an ideal gas with a temperature of that? Right, to do this one, I used this equation here. So you could do it other ways. So this is the mass of a, this is the energy, the internal energy of a single molecule. So the energy of a molecule is equal to 3RT over 2Na. Right, so then all we need to do is times by the number of molecules to find the total energy. So the total energy is equal to the number of molecules times by that, and the number of molecules is the number of moles times by Avogadro's number. So my Avogadro's numbers cancel, and I've just got that. So I've got 3 over 2 times by 8.31, which is the molar gas constant there, times by T, 15 degrees Celsius is, we've got to work in Kelvin, 288 Kelvin, divided by, no, we don't have anything else on the bottom, we've got to times by the number of moles, 2.4 there. So we've got 3 divided by 2 times by 8.31 times by 288 times by 2.4 is equal to 8,000. Is that one there? Okay, maybe other ways you can do that one. That's the way that sprang out is easiest for me. Question 12. We've got one of these questions where you have to work out the place between two objects which has no net field, so the pull from each one is equal. So the first thing that we know is it's got to be closer to Charon than it does to Pluto, because this has a smaller mass. Right, so let's think about the size of the field. So I'm going to work in terms of the force due to the field. So G, if I put a little mass m there, so Gmm over r squared. Now the distance from there to there, if I call this m here, the distance from there to there is going to be called x, is equal to the, so that's the force on this particle from this one. Now I want to do the force on this particle from this one. So it's G, its new mass, which is m over 9, that's the mass of this one, times by the mass of the little thing that I've shoved in the middle. And this distance here is d minus x. So that's d minus x squared. Right, loads of this stuff cancels. The g, the m, and that m all cancel. And I've got 1 over x squared is equal to 1 over 9 times by d minus x squared. So if I square root this all, I've got 1 over x is equal to 1 over 3, just put this on there as well, d minus x. So move that up there and I get d minus x over x is equal to 1 over 3. So what's this telling me? This is telling me that this distance here is 3 parts and this distance here is 1 part. So for every part that this one is 1. So the distance here must be 3/4 of d, and the distance here must be 1 over 4d. You can continue to solve it if you want. You just multiply that up there, and you get 3d minus 3x is equal to x. So therefore, bring that over there, 4x is equal to 3d, so x is equal to 3 over 4d. So that's how you would brute force it through, but you can tell from this bit what the ratio is. You know that this is 1 part to 3 parts there. So what's the answer? C, isn't it? The distance between the Sun and Mars varies from this distance to this distance. When Mars is closest to the Sun, the force of gravitational attraction on is F. What's the force going to be when they're further apart? Well, for a start, it's going to be smaller, isn't it? So it's going to be one of those two. So if you know, worst you can do is guess there. You've got a 50-50 chance. Right. F, the force, is inversely proportional to the distance squared. So that means that the new force is going to equal the old force times by a ratio of these squares, and we want to make it smaller than 1, so we need to put the bigger one on the bottom. 2.5 times 10 to the 11 squared and 2.1 times 10 to the 11 squared there. Obviously those bits cancel each other out, and you're left with 2.1 squared divided by 2.5 squared. That gives you that fraction there, so it's 0.71, which is A there. You could again work that out in a more thorough way using the equations, but the nature of a multi-choice question is you don't need to go through all of those steps. You can just shortcut to the answer like I did there. So what I did was I first of all determined that, just by intuition, that it was going to have to be a smaller value, so it's going to be one of these two, and then I knew that it was a square relationship, an inverse square, so I put the larger one of these on the bottom, smaller one on the top, squared them up, and that was the fraction that I got. Okay, this question here, we have to equate the centripetal force, mv squared over r, to the gravitational force, which is providing that centripetal force. Okay, so one of our r's cancel, the m cancels there, and I got v squared is equal to gm, but I don't want v squared, I want kinetic energy. So I want a half m times by all of that over there, which means I need a half m times by all of that over there. So I've got m, and g on the top, and I've got 2r on the bottom, so it's a there. You see what I did there? So I got my v squared, I cancelled it for v squared, and then I just put in a half m on this side and a half m on that side to turn this side into kinetic energy. So that side must also therefore be kinetic energy. Okay. Question 15. So you can see this one straight away. It's asking what the field is in this capacitor. The field inside a capacitor, the whole point of it is that it's a constant field. So we want something that's constant. So it's that one there. If we were to plot the potential, then the potential would look like that. Okay, but the field is just constant all the way through. Particle of mass m, charge q is accelerated through a potential difference of v. That means it's got qv as its speed, as its kinetic energy. So a half mv squared is equal to q times by big V, the potential it's been accelerated over. Right, what is the acceleration of the particle? Okay, so we're going to combine this with Suvat now. So we need a Suvat equation that doesn't involve time, so we want v squared is equal to u squared plus 2as. And there, you'll notice that u is 0, so we don't even need that if I put that off the top of the page. So I have v squared equals u squared plus 2as. U is 0, so we don't need that. So we're going to get v squared is equal to 2as. So have a look here. We can rearrange this for v squared. V squared is equal to 2q big V over m, and that is equal to 2as. 2a times by s, which is in this case d. So that cancels with that. The d moves to there. So we get qv over md, which is that one. An electron moves through a distance of that parallel to the field of force that. What's the work done? Well, the work done on anything is equal to the force times by the distance moved in the direction of the force. So the force is the electric field strength times by q. The distance is still d, and I think we've got everything now. Yeah. So we can just shove all that into the calculator, and we have 2,000. Watch units on multi-choice, they like to change units around. Times by q, 1.6 times 10 to the minus 19 times by 0.1 is equal to this here. Now notice that the direction it moves through is parallel to the field lines. If it was perpendicular to the field lines, no work would be done. Okay. Parallel plate capacitor is fully charged, then disconnected from the power supply. A dielectric is then inserted once it's been charged. So we are looking at this equation here partly, and we need to think of what's going on inside this capacitor. So if we charge up the capacitor over here, and then we disconnect it, the charges are stuck now, they can't move anywhere. So the charge stays the same, so it's got to be one of those two there. Now we need to think about what's going to happen to the electric field strength if the capacitor, if we put something dielectric between there. Well, if we put a dielectric between there, then according to this equation down here, the relative permittivity of the dielectric is going to be larger than 1, which means we're going to increase the capacitance. So the capacitance goes up. Now, Q is equal to CV. If the capacitance goes up, then and the charge stays the same, then the potential difference has to drop. The electric field across a parallel plate capacitor is, it's not D over V, it's V over D. So if that drops there and that stays the same, then that must also drop. So it's got to be this one. There's quite a lot of things to think about on that one. This one, a capacitor C stores a charge Q. Potential difference on the plate is doubled. What is the change in the energy stored on the capacitor? This is, it doesn't say what's the new energy stored on the capacitor, it's what the change is. So the energy stored on a capacitor is equal to a half CV squared, and we also know that Q is equal to CV. Capacitor is the same, so if we double the potential, we're also going to double the charge. This does not have V in it, so I'm going to eliminate V from my question from this here. So we've got Q squared over C squared. So what am I using here? I'm using energy stored on the capacitor, which is this one here. I always remember it as this one, so I've just worked out that one, but you can actually just get that straight off the formula sheet. There it is. That squared cancels with that, which gives you the energy stored on the capacitor is a half Q squared over C. Okay, if we double the voltage, then we quadruple the energy. So the new energy on the capacitor would be 4 times by a half Q squared over C. And the difference between that and that is 3 halves Q squared over C, which is that one there. Capacitor consists of 2 parallel plates. We're going to need this here. C is equal to A epsilon naught epsilon R over D. Right. If we double the length of the square sides, then we're going to times the area by 4, so that's going to increase the capacitance 4 times. If we halve the distance, then because we're dividing by distance, a smaller distance increases the capacitance, so that's also going to times the capacitance by 2. So we're going to have an 8-fold increase in the capacitance, so it will be that one there. a capacitor of capacitance, this is charged and then discharged through resistor that. So first of all we should work out what RC is. So RC, the time constant, is going to equal 120 times 10 to the minus 6 times by 20 times 10 to the 3 there. So let's just work that out. 120 times 10 to the minus 6 times by 20 times 10 to the plus 3, which is 2.4 seconds. Okay, now we can use this equation here, V equals V naught, e to the minus t over RC, and we just set V naught is equal to 1, so V is equal to 1 times by e to the minus, the time is 4.8 over the time constant is 2.4. So solve this, we get that's e to the minus 2, which is 13%, so it's that one there. However, there is a shortcut. As soon as you've got to this point here, you know that in one time constant the capacitor will discharge to 37% of its original value. That's the sort of standard rule that you should learn, and that's because it's 1 over e. If I do e to the power minus 1, I get 37%. So you know in one time constant it'll go to 37%, or about a third. So in two time constants it'll go to a third of a third. There's only one of these which is smaller than a third, so it's got to be that one. So you can, once you've worked that out, shortcut straight to the answer there, or you can just work it out all the way through. Right, question 22 is a changing flux one. So the thing that we need is the induced EMF is equal to minus, in brackets, the change in linked flux divided by the time it takes for that change. So where am I getting that from? I'm getting it from the magnetic fields section, which is all over the page. Getting it from the magnetic field section, which is there. Okay, that bit there, I've just written it slightly differently. I've put the N inside there. It's the same deal. Okay, so first of all we need to find out the magnetic flux linkage here is at a maximum. The magnetic flux linkage here is 0 because the field lines do not cut through the area of the wire loop. So let's work out what the magnetic flux linkage is. So phi times by n, the flux linkage, is equal to the flux cutting through 1 times by the number of turns. So that's equal to B is 90 times 10 to the minus 3 times by the area. Right, the area we've got to do pi r squared. So that's pi times by r is going to be 30 times 10 to the minus 3 millimeters squared. And then we need to times by the number of turns, which is 20. So let's work that out first of all. So we've got 90 exponent minus 3 times by pi times by 30 exponent minus 3, and we square that because that's pi r squared, times by 20 gives us, I'll write that down, 5.0893 times 10 to the minus 3, and that's in Weber. Okay, we now need to use this, so we need to divide it by the time it took for that change, which must be somewhere, here it is, 90 degrees, so it's gone from maximum to 0 in 0.2 seconds, so we divide it by 0.2, gives us 25 millivolts, which is that one there. The mean power dissipated in a resistor, okay, so P is equal to IV in general. So in this one we're trying to find the peak current in the resistor. Well, what I'm going to do first is I'm going to find the RMS current inside the resistor. So the mean power dissipated is when you multiply the RMS versions of these two quantities together. So here goes. We want to find out the current, so I RMS is equal to P average divided by V RMS. So we do this. P average is 47.5 exponent minus 6. I want to divide that by 150 exponent minus 3, and we get that many microamps. Then we need to change that to a peak. So we times it by root of 2, and that gives us that one there. National grid is used to travel, right, so you should know high transmission voltage, low current. And the reason for that is I squared R wastages. You want the current in the wires to be as low as possible. Mains transformer has primary of this and secondary of that, blah blah blah. Transformers, what's the peak power transmitted? Right, okay, so this is similar to this one. So what we're going to do first of all is work out what the voltage at the secondary is. So V secondary. So that's going to be V primary times by NS over NP, because it's a step down. So we're going to have 230 times by 130 divided by 2,500 gives you that's an RMS, of course, of about 12 volts. So 12 volts, that P is equal to R, V squared over R, so we need to square that, divided by the resistance of 6, and we get 23 watts. Now, be careful, it's not that one, because we have worked out the average, because that was an RMS value there. The peak power is double that, so it's going to be that one. Because, if you think about going back to this equation here, if we go peak is equal to I peak, which is I RMS times by root 2, V peak, which is V RMS times by root 2, and root 2 times by root 2 means you've got 2, and I RMS times by V RMS was P average, which is the same as 2P average. So it's this one. Rutherford scattering led to the discovery of the nucleus. Not much in it in that one. Question 27, we've got a source, we're blasting it through these different materials. Paper has no effect, that means does not contain alpha particles. So it's not that one, it's not that one, it's not that one. It must be that one, there's nothing else that you need to worry about. An element, however you pronounce it, has a half-life of 3,500 seconds. What's the decay constant? So this lambda equals ln of 2 over t half. And we just need to make sure that we put our t a half in the same units that we end up with here. So we just got ln of 2 divided by 3,500. It's nice to know that some of them are reasonably straightforward. Which is that one B. A pure sample of nuclide X has N nuclei and an activity of A. The half-life is 6,000 years. A pure sample of nuclei Y has 3 times as many nuclei and 6 times the activity. So if it had the same number of nuclei, the activity would be 2A, because we just take a third of this sample and we get 2A. So what's the half-life of the nuclide? If we double the activity, we halve the half-life. Simple as that. So it's that one there. mathematically speaking, you're working it out using that. You've got the half-life from there as well, so you can work it out from that. Now, double the activity means you use up everything twice as quickly. 30. Cobalt-60 has a half-life of 5.27 years. What's the total activity of 1 gram of cobalt-60? So we need that equation I just showed. A is equal to lambda, which is ln of 2 divided by t a half, times by n. But n is the number of atoms, so that's the number of moles, which is m over mr, times by Avogadro's number there. Right, we know all of this, so let's put it all into our calculator now. So we've got ln of 2 divided by, we need to put the half-life in. So 5.27, 365-ish days in a year, 24 hours in a day, and 3,600 seconds in an hour. So far I've done that bit of the calculation. Now I need to times by the mass, so the mass was 1. Then we need to divide by the relative atomic mass, which was 60. Then I need to times by Avogadro's number, which is that. So it is A. That many becquerel. Last couple of questions then. We're looking at this equation here, which is saying that the mass of the particle is proportional to the radius cubed. So we have the mass of iron over the radius of iron cubed is equal to the mass of uranium over the radius of uranium cubed. So rearrange that for the Ru cubed is equal to the mass of uranium over the mass of iron. I'm just going to give a number bigger than 1, so that's good. It's going to increase the radius, and then times by the mass, the radius of iron cubed. Okay, so all I've done there is I've used this equation here. I'll show you what I've done in more detail. So we had R is equal to R naught A times by to the power of third. So I want to rearrange that to get a constant equal something. Just cube it all. Like that, and so that is the same then for every single particle there is, every single nuclei that there is. Okay, so that's the first one. I've put it the other way up here, but never mind. Right, so we just need to shove that in the calculator now. So we have 238 divided by 56, 238 divided by 56, this number of protons doesn't matter, times by this 4.35. I'll put the times 10 to the minus 15s in, but you don't need to. Let's just put all this in brackets. If I'm going to do this, is equal to that. So that's that side. And we need to cube root that. So just do that to the power. And I get that, which is that one there. Right, finally, uranium undergoes a nuclear fission to produce these two daughter nuclei and 3 free neutrons. What's the energy released on this process? What we need is the difference in binding energies per nucleon of these two compared with this one here. So we just add up the binding energies of these ones. So we've got 8.6 is the binding energy per nucleon of that one. There are 89 nucleons. Plus 8.3 times by, and there are 144 of those. The binding energy of neutrons is 0. And then we take that away from, because they're separate, they're not bound to anything, so they obviously don't have a binding energy. Gives you 190 of whatever these is, MeVs, so it's that one there. Okay, well I hope you found that useful. If you did, then please do share it. Good luck in your exams.